Welcome everyone to the second part of this DFT introduction lecture. This time we discuss a more from theory to practice approach. In the first lecture we covered quite a lot of theory, Schrödinger equation, then going from the wave function to the electronic density. We discussed the Hohenberg-Kohn theorems, and last but not least the Kohn-Charm formalism and how to end up with the Kohn-Charm equations. So in this lecture, which consists also 5 parts, first of all we discuss the exchange correlation functionals. So when we discussed the Kohn-Charm formalism and ended with the Kohn-Charm equations, we discussed that there is a term, the exchange correlation functional, where we gather all the contributions, electron interactions, electron exchange and electron correlation, and also the contribution made by the assumption that we can compute the kinetic energies from a non-interacting electron, from non-interacting electrons. Those are all combined in the exchange correlation functionals, and we stopped our discussion there that we need approximations to solve it. So in this first part we will actually discuss different methods to solve the exchange correlation functional. Where in that sense we will also discuss the concept of the Jacob's ladder, which gives us a picture to describe various exchange correlation functional methods, because they differ in their chemical accuracy but also in the computational costs. In that regard, we will discuss in the second part the local density approximation, or short LDA, and the generalized gradient approximation, or GGA in short, which are basically the rung 1 and rung 2 within those Jacob's ladder scheme. Both are quite commonly used in the material science community, and for that reason we discuss them to provide you a better understanding how they work, and then what they can be used for and what they can't be used for. A bit in that sense we discuss in the third part and dispersion interactions, and the need to correct them in DFT, because as you can imagine that having whatever 2 benzene molecules stuck over each other, there's a huge dispersion interaction contributions between those 2 molecules, and DFT is quite famous for underestimating dispersion interactions. So there is actually a strong need to correct dispersion interactions in DFT. So we will discuss different approaches in the third part, and then the fourth part is actually the practical implementation or informations on how to run the DFT calculations, and then also in that sense how the self-consistent field method works, because we have to iterative solve the Kohn-Charm equation to actually obtain the true ground state density and then to obtain the ground state energy. And last but not least, we will discuss a more hands-on example. So we will discuss electronic structures in molecules and solid states, because until now, right, we just then discussed how it works in practice, what we can do, what's the theory behind it. But in the last part we will give you some examples what you can actually compute with DFT, what actually DFT is capable to output on a molecular and solid state level. So what it can be used for molecules and what it can be used for solid states. Okay, but starting with the first part of today's lecture with the exchange correlation functional. So where did we left the Cohen-Charm formalism? So we left them with the Cohen-Charm equation. We pointed out that the Cohen-Charm equation is basically a single particle Hamiltonian, a single particle Schrödinger equation, and the party in brackets is the single particle Hamiltonian. And the last part of that Hamiltonian is the exchange correlation functional, which consists out of 3 contributions. The first one is the difference between the Cohen-Charm kinetic energy and the true kinetic energy of a multi interacting electron system, whereas the Cohen-Charm only treats the electron as non-interacting. The second part is the exchange contribution, and the last part the correlation, electron correlation contribution. Okay, so we stopped in our discussion that various approximations can be made to compute the exchange correlation functional, and that's where the picture from the Jacob's ladder come in, because those different approximations they differ in their chemical accuracy, but also in their computational effort. So usually having an approximation which is more accurate also needs more computational effort. And to describe that correlation between accuracy and computational effort, Perry and Schmidt, who described that in their paper, came up with the biblical image of the Jacob's ladder described in Genesis 28, where Jacob basically walks upwards a ladder from heaven, from the earth towards the heaven, and they used the exact similar way to describe the correlation in DFT exchange correlation functionals, because every single ladder, or every single step on the ladder brings you closer to the chemical heaven, or to the heaven of chemical accuracy. So the ladder connects the Hartree world, or sometimes called Hartree hell, with the heaven of chemical accuracy. So the overall goal is to achieve chemical accuracy, which is usually defined as 1 kilocal per mole. I'm sorry for now mixing a couple of units. Chemists love kilocal per mole or kilojoule per mole. So 1 kilocal per mole usually equals to 45 millielectron volts for energetic properties, or then 0.1 to 2.2 kilocal per mole for reaction energies. And as I said, each level or rungs brings you closer to achieve that goal, to achieve the chemical heaven. And we have on that ladder 5 different rungs. And the first level or rung is basically the worst, and then it increases in accuracy, but also the costs. Okay, what are those rungs? So on the first, we have the local density approximation LDA, which only depends on the electron density. And some example here is PW92. That's quite known. On the second rung, we have the generalized gradient approximation, or GGA in short, which depends on the derivative of the electronic density. An example here is PBE, which we then also later use in the tutorials. On the third rank, we have the meter GGA. It depends on the second derivative of the electronic density. A good example here is the scan, which is quite known, or the R2 scan, which is a newer development of that. On the fourth rank, we then have the hybrids. They now add some Hartree-Fock exchange to the functional, and what that provides us with occupied orbitals. And for that, we describe for example, band gaps more accurate. And a good example here is PB0 or the HSE06, which are quite known and famous in the material science community. And lastly, we have the double hybrids, which further extends the hybrids plus the perturbation theory correction. So to speak, they add unoccupied orbitals. Because DFT is a ground state method, we're not good in treating unoccupied states. So we're anyhow just good in treating occupied states. So double hybrids add unoccupied states, but they increase the costs, as we will see later. So what those different ranks can actually be used for. So LDA is quite simple, and it describes the system more in this homogeneous electron gas field or method. So for that, it's quite good for simple for simple metallic systems, which anyhow have a lot of delocalized electrons, so they are smeared all over the system, so it comes close to an homogeneous electron gas. However, molecules are usually not distributing all their electrons over the system. They're usually quite bounded to one of, like an hydrogen, like an water molecule, right? The oxygen binds quite strongly the electrons, so those electrons are not delocalized, they are localized towards oxygen. So for that reason, LD is quite bad or unsuitable for molecules. The second ring we have GGA, which is quite okay for molecules and solid. It describes, for example, bond distance quite well. It describes bond angles quite well, lattice parameters, but it's not great for band gaps and dispersion interactions. Those are underestimated. The third rank is the meter GGA, which basically lies between hybrids and GGA. That's a pro and a con. So it deals with a lot of things, good and bad in the same time. On the fourth rank we have the hybrids, which now quite okay with, on the pro side, with dealing with charged localizations, and for that also they are good with band gaps, but still they underestimate dispersion interactions. And then lastly we have the double hybrids, which are now again good with charged localizations and also with non-local interactions like the dispersion interactions. So double hybrids actually includes dispersion interactions. Again, that's the reason why we later talk about dispersion interaction corrections. How about the costs? What are the costs of the different rungs basically? So LDA comes with a third order. So it scales with the third order of the electrons. So it's similar to the Hartree-Fock if you know some quantum chemistry. GGA is not really that far from LDA, right? It was more like LDA was, because we started from a homogeneous electron gas, and it was the first step to implement that one was the LDA, and then the next improvement was to take the derivative of the gradient into it. So for that reason it's more or less similar to LDA. It scales also with the third order. Meter GGA, again third order, but a bit higher than GGA. And the hybrids then scale with the fourth order, and then the double hybrids with the fifth order. So those are really expensive. And then you have to think about which system size you can be used, right? Which, depending on your electrons in your system, which you can treat with which method. So taking double hybrids to larger systems is nearly impossible. Or I mean, you pay a price, right? If you're willing to pay the computational cost, you can do that. But usually I would say the LDA and GGA are quite commonly used hybrids for on top calculations. We can discuss that later with the within the practical informations. And then exactly. To give you an example how the Jacob's ladder work, there's this nice article in PCCP from 2011 by Lars Gorik and Stefan Grimmer. I can highly recommend you that. And they did some tests on the VT-MAD, which is weighted mean absolute deviation. They had a small data set, and then they tested it for various thermochemistry, kinetics, and non-covalent interactions, like band formation energies, reaction barriers, dispersion interactions, stuff like that, for the 5 different rungs of the Jacob's ladder. So in black we have LDA, then in gray we have the GJAs, the cross pattern is meter GJA, the stripped are the hybrids, and blank is the double hybrids. And what we see, if we check on the left hand side, you see all different the different functionals they used. When we had, for example, there's a PBE at some point. Here's a PBE Sol, which is a opt version for solids. There's a normal PBE. That's the SVWN. That's quite a known LDA, for example, and so on and so forth. We don't have to check all of them, but you see a clear decrease, right? You see a decrease from LDA towards the double hybrids, and then on the right hand side we have the average values. So you see basically that LDA has an average error of 12 kilocal per mole, or deviation basically, and that it decreases to 1.8 for the double hybrids. But what you also see is that by just taking the derivative of the density into account in GGA, you halve the error, right, from 12 to 5.3. The meter GGAs are slightly lower in the error range than the GGA. And then the hybrids, I mean, it's noticeable, right? Don't get me wrong. The error gets noticeably reduced, but you pay a price. And then the double hybrids, I mean, lower the error by a factor of 2 from the hybrids, or factor 3 from GGA, but with way more additional computational costs. So depending on the question you want to answer, you have to also choose your exchange correlation functional. I mean, it depends on one hand on your material system. Can you actually use a hybrid, for example, for your system? But also, do I need the additional accuracy, and do I'm willing to pay the computational price for that? So we discussed the different exchange correlation functional implementations and the concept of the Jacob's ladder. And in the next part we will actually discuss the local density approximation and generalized gradient approximation in a bit more depth.